Okay, so today we're going to look at formulas of compounds, and there are three different types of formulas that a question could be talking about. The first one is empirical. An empirical formula is obtained by an experiment. It shows the smallest whole number ratio, and we do that mathematically with the data. We take our grams, we turn them into moles, we divide by the smallest, and that determines the ratio. A molecular formula shows how many are actually in the compound. So this is where we take the molecular formula that is given to us, we divide it by the empirical formula, and then take that multiple and multiply the subscripts by it. A structural formula shows the arrangement of the atoms and the bonds. So here you can see the structural formula of caffeine. And then you have a ball and stick model of these different compounds. You have an empirical formula of HO, but a molecular formula of H2O2, so it's hydrogen peroxide. So structural formulas we really won't get into in this unit. We'll save that for later. We're really going to focus in on the empirical and molecular. Hydrates. Hydrates are ionic compounds that contain water. Hydrates are compounds that contain water. And so if we wanted to figure out the number of water molecules, we would take the moles of water and we would divide it by the moles of the anhydrous. So really this should say the moles of hydrate, so the salt with the water, divided by the anhydrous salt. And we're going to be looking at one of those examples as well. All right, so here are the steps for finding empirical and molecular. And these are the same steps that we had last year in Chem 1. So first we find the moles of the element. So if you don't have a periodic table, you might want to pause and grab that. Find the ratio by dividing each of them by the smallest moles. Watch out for 0.5. You have to multiply everybody by 2. And then 0.3 or 0.6, you're going to multiply everybody by 3. And we will see some of those examples. Those ratios tell you what the subscripts should be. All right, so let's talk about what that percent actually is. It's the percent composition. So anytime you see percent composition or percent by mass, what you're going to do is you're going to take the mass of the element or ion or polyatomic or water, whatever it is that they want the percent of. And you're going to divide it by the mass of the whole compound. And then multiply by 100 to make it a percent. In Chem 1, we would say the part over the whole times 100. So nice and simple. So if we take ammonium nitrate, and we add together all of the masses, this whole thing has a mass of 79.05 as its relative molar mass. So to find nitrogen's percent, we would take the mass of nitrogen. Now there's 2 nitrogens, so we would have to do that mass twice, divided by the mass of the whole thing times 100. And we would have 35.4% nitrogen. For percents, you need to go to at least 1 decimal place. All right, so then let's look at our hydrogens. We have 3 hydrogens. So we do 3 times the mass of hydrogen divided by the total mass times 100. And we get 3.8%. So to find oxygen, we could go the same process, 3 times the mass of oxygen divided by that. Or we also know that percents always add up to be 100. So if we subtract the percent that was nitrogen and subtract the percent that was hydrogen, we would be left over with the percent that is oxygen. So oxygen would be 60.8%. Okay, so here we're looking at finding the empirical and molecular formulas. So it tells us that the weak acid has a molar mass of this, so we're going to use this for when we find the molecular formula, because this would be our molecular molar mass. It says upon analysis of this small sample, so this amount of grams would be for hydrogen, phosphorus, and oxygen put together. And then we have our masses of just hydrogen and phosphorus. The remainder is oxygen. So what we can do is we can take that total and we can subtract our masses of hydrogen and phosphorus, and we would have the mass of just the oxygen. Whoops. So this is the remainder, so that's the mass of oxygen. So what we're going to do, the first step, is to take our masses and convert them into moles. So the unit and the substance are brought down to the bottom, and we're trying to go to moles, 1 mole, and then the mass is the molar mass. So we look on the periodic table, 1.01. We want to use the same number of significant figures, so that would be 3. So that 0, remember, is not significant. We have our moles of hydrogen. We're going to do the same thing for the phosphorus. Grams of phosphorus on the bottom, moles of phosphorus on the top, 1 mole, and then the molar mass from the periodic table. Keeping our significant figures the same, which would be 4. And then our remainder, which was oxygen. Bring our unit and substance to the bottom. We're going to moles, 1 mole, molar mass, and keeping our significant figures the same would be 6, 7. All right, so then what we're going to do is we are going to divide by the smallest amount of moles. So out of all of these, the smallest is phosphorus. So we're going to divide all of them by phosphorus. So we have 1 phosphorus. That rounds to 2 hydrogen. So this is where we want to round it to a whole number for that ratio. Just watch out for the 0.5. You can't round to 0.5 or a 0.3 or a 0.6. So this gives us exactly 3. So the empirical formula would be H2PO3. So to find the molecular formula, let me change colors. We would want to divide the molar masses. So we take the molar mass that's given to us in the problem, and we divide it by the molar mass of H2PO3. So 2 hydrogens, a sulfur, and 3 oxygens, and we get a molar mass of 80.99 grams per mole. So when we divide that, we get a multiple of 2. So the molecular formula is twice that of the empirical. So we're going to multiply our subscripts by 2. So we have H4P2 0.06. All right, looking at another example. After combustion with excess oxygen, this mass of the petroleum produces carbon dioxide and water. So this is a little bit different in that it tells us what the mass of the compounds are. So we have the petroleum, and it's reacting with excess oxygen, and since it's a combustion, it's going to form CO2 and water. So what this is telling you is that the carbon from the petroleum is going into the carbon dioxide, and all of the hydrogen in water came from the petroleum. So all of the carbon and all of the hydrogen are coming from the petroleum. So if I know how much carbon is in this carbon dioxide, then I know how much carbon was in the petroleum. If I know how much hydrogen is in this amount of water, then I know how many hydrogen was in the petroleum. So you don't have to have a balanced reaction, you just need to understand that that's where all of this is coming from. So when we say we have, sorry, I need to find my mouse, 38.196 grams of carbon dioxide, I'm going to find out how many moles of carbon are there, because that would equal the moles of carbon in the petroleum. So we bring down our units, grams of carbon dioxide. We are going to go to moles of carbon dioxide. So the molar mass of carbon dioxide is 44.01, and that's for 1 mole. So grams of carbon dioxide cancel. Then we need to set up a mole ratio, because remember, it's not moles of carbon or carbon dioxide that we want, it's the moles of carbon. So we're going to say 1 mole of carbon dioxide is 1 mole of carbon, because there's 1 carbon in carbon dioxide. So then the moles of carbon dioxide cancel. And then keeping our significant figures, 8, 6, 7, 8, 9 moles of carbon. So again, because the petroleum is the only place where there would be carbon, this amount of carbon then has to come from the petroleum. We're going to do the same thing with the hydrogen, because the only place the hydrogen can come from is the petroleum. So 23.433 grams of water, molar mass of water, 18.02, is 1 mole. So our grams of water would cancel. Then we're going to set up that ratio to see how many moles of hydrogen there are. So for every 1 water, we're getting 2 hydrogens, right? Because there's 2 hydrogens for every water. So then our moles of water would cancel. Again, keeping our significant figures the same. All right, so then we're going to divide by the smallest, and the smallest is carbon. So we have 1 carbon in our petroleum, and we're going to divide hydrogen. And we have 3, that rounds nicely to 3 hydrogens. So the empirical formula for the petroleum is CH3. So again, the reason we can do that is because all of the carbon and all of the hydrogen on the product side could only come from the petroleum. All right, looking at another example. We have a biochemical substance that contains only carbon, hydrogen, and oxygen. It's being burned in the atmosphere. So we have this biochemical again, reacting with oxygen. It's burning, so we know it's combustion, so it's going to form CO2 and H2O. So all of the carbon and carbon dioxide is coming from that biocarbon. All of the hydrogen from the water, or all of the hydrogen in the water, is coming from that biochemical. Now we cannot say the same thing for the oxygen because we're adding more oxygen on the reactant side. So we're going to have to find oxygen a little bit different. So the first thing we want to do is take our grams of carbon dioxide and find out how many moles of carbon we would have. So we would bring down grams of carbon dioxide. We're converting that to moles. So 1 mole and then the molar mass. So grams would cancel. Now we need to go from moles of carbon dioxide to moles of carbon. So we would bring down moles of CO2 and we want moles of C. For every 1 carbon dioxide, we have 1 carbon. Keeping our significant figures the same. All right, we're going to do the same thing for the water. So we have 7.749 grams. And remember, the only thing that is coming from the biochemical alone is the hydrogen. Oxygen doesn't work this way. We'll have to do something different for the oxygen. So we're going to convert our grams of water to moles of water. And then for every 1 water, we have 2 hydrogens because of that subscript. So grams of water would cancel, moles of water would cancel, and we're left with hydrogen. Keeping our significant figures the same. Okay, so now we have to worry about the oxygen. Well, we know this amount right here, this 12.915, is carbon and hydrogen and oxygen all together. So if I take that total and I subtract the mass of carbon, then I'll know how many grams of carbon I can subtract grams of carbon and grams of hydrogen. I would know how many grams of oxygen I would have. So we're going to do a conversion off to the side here. We're going to convert this to grams. And we get 5.16, keeping our sig figs the same here, 91 grams. So we can subtract that mass of carbon, and then we're going to do the same thing for the hydrogen. So 1 mole of hydrogen, molar mass of hydrogen. Notice that it's not a diatomic because it's in a compound. So we're going to subtract that down here as well. All right, so that will give us the mass of hydrogen or oxygen. So you can't use carbon dioxide or water to figure out your mass of oxygen because oxygen is coming from both the biochemical and the excess oxygen. So the only way to figure out how much oxygen you have is to subtract. So that gives us grams, but we need to convert to moles. So then we're going to convert from grams of oxygen to moles of oxygen. keeping our significant figures the same. All right, then once you're in moles, you divide by the smallest. So let's ignore the stuff written in blue. We're only looking at the moles now, the stuff in red. So which one is the smallest? Well, oxygen is just smaller, that should be a 2, just smaller than our carbon. So we'll use the value for oxygen. So we have 1 oxygen, and when we divide this up here, that would give us 1 carbon, and we're going to divide the hydrogen. And that gives us 2 hydrogen. So our empirical formula would be C1H2O1. To find, oh, that's it. So that's the empirical formula. So there's our answer. Now I know this one is a little bit tricky to grasp, so we will be doing more of these in our examples in class, and then you'll work a couple as your classwork. All right, so then let's look at a hydrate problem. So here we have the mass of a hydrate. So this would be nickel sulfate and some amount of water. We just don't know how much water. And then it says after heating it has this mass. Well, if you think about it, if something has water and you heat it, the water is going to evaporate off. So this 10.37 grams would represent the mass of the anhydrous, or just the nickel sulfate. So we have the mass of the nickel sulfate with water, and we have the mass of just the nickel sulfate because we've heated off the water. So can we figure out how much water there would be? Well, yeah, we can, because we can just subtract them. So we would have 20 grams of the nickel sulfate with some amount of water, and we're going to subtract the mass of just the nickel sulfate. And we would have a mass of 9.6 for the amount of water. We just don't know how much water it is. Now I only went to 1 decimal place because when you add and subtract, you want the fewest decimal places. All right, so then what we want to do is we want to figure out the mole ratio. So we want to convert our nickel sulfate to moles, and we want to convert our water to moles. So we're going to say 10.37 grams of the nickel sulfate. Bring your unit to the bottom. We're converting it to moles. 1 mole, and then we need to add together the molar mass of the nickel sulfate. So the mass of nickel, sulfur, and 4 oxygen is 154.76. So we would divide that, keeping our significant figures the same. And then we'll do the same thing for our water. Now the moles of water should always be, oh I'm sorry, we only need 2 significant figures. The moles of water should always be more than the moles of the salt, the nickel sulfate in this case, because we know that there should only be 1 NiSO4, and then we're looking for how many more waters there would be. So water should always be the larger value, so that when you go to divide by the smallest moles, you would always be dividing by the salt. So this should always be 1. And then we're going to divide by the moles of the salt. and we have 8 waters. So the formula would be NiSO4.8H2O. But the question is really saying determine the hydrate's name. So then we have to name this. So we know Ni is nickel. Because there's no subscript for the nickel or the sulfate, right? SO4's polyatomic should be in parentheses. That means they have the same charge. And so we know sulfate has a charge of 2. And since there's not a subscript of 2 on the nickel, that means that nickel was also 2, so that it was reduced. So this is nickel 2 sulfate. Then we use the prefix for 8, which is octa, and water is hydrate. So this is nickel 2 sulfate octahydrate. All right, and then one more example using the hydrate. So we have cobalt 2 chloride, so CoCl2, crossing our charges, hydrate, so we don't know how much water there is. And then we have the anhydrate, which means this without the water. So this would just be the cobalt chloride. And we want to know what the formula is. So the first thing that we're going to do is we are going to subtract to figure out how much water we have. And so we have 2.50 grams of water. I put the 0 there so that it matched the significant figures. And then we're going to take our masses and we're going to convert them to moles. So we take the mass of the anhydrate and we're going to convert it to moles. So we need to add the molar masses. $129.83. And keeping our significant figures the same. Then we're going to do the same thing for our water. Keeping our significant figures. Notice again that water has the higher amount of moles because we always want the salt to be the smallest, so that when we divide by the smallest amount of moles, the salt's always 1. And so that would round nicely to a 2. So the formula, cobalt 2 chloride times 2 waters.